Hello, everyone. My name is Nilesh Savargaonkar, and I work for ExxonMobil Chemical Company as part of the polyethylene customer application development group. Today, I'm going to present the work we did in collaboration with WNH. This work was focused on the use of our metallocene polyethylene resins, or what we call as performance polyethylene resins, in order to reduce the nylon content in cast barrier films. This work was driven by the sustainability initiatives in the food packaging industry. Let's talk a little bit about the barrier films that are used for meat and cheese packaging. Many of these films are highly complex structures, and they typically contain 7, 9, 11, or more layers in the structures. The films can be made by a variety of processes, such as regular cast films or regular blown films, or the downward extruded water quench films, and sometimes even more complicated processes like double or triple bubble films. And in many cases, these films go through a downstream conversion process, such as thermoforming, to make the bottom webs of processed meat and cheese packages, like the hot dog and the turkey package shown in the picture here. And sometimes they go through a lamination process, such as adhesive lamination or extrusion lamination, or making lidding films or conversion into pouches. In this presentation, I'm going to focus mainly on the film structures that are made for thermoformable bottom webs, like the hot dog and the turkey package shown here. As I mentioned earlier, these can be made by different processes, such as regular cast films, or regular blown films, or water quench films. In US, Canada, and Europe, cast films seem to enjoy a higher market share for multiple reasons. One of them is formability itself, since the cast films are easier to undergo solid state orientation via thermoforming. These cast films also have better optical properties, such as low haze and higher clarity, so that consumers can clearly see the package, the food package inside easily. And the run size for cast films typically tend to be large, which are more suited for these type of structures. The films can also be made by blown film or water quench processes, but they seem to have a smaller share in US, Canada, and Europe. As far as the market size for processed meat and cheese, which includes thermoforming, but other converting processes as well, is fairly large in US and Canada. And the growth rate is projected to be at 3 to 4%, which is a decent growth rate for this market. As far as the market size, the higher alpha olefin polyethylenes are estimated to have a market size of 18.5 KT, or about 40 million pounds. And other polyethylenes have estimated market size of 72 KT, or close to 160 million pounds. Now let's talk a little bit about the objectives behind this study. The film structures used here have fairly large nylon content, anywhere from 20 to 40% nylon, which makes them very difficult to recycle, both by mechanical recycling or chemical or advanced recycling processes. Hence, the film converters and brand owners in this market have expressed the desire to reduce the nylon content by 25 to 50%. Many players in the value chain have set up certain sustainability goals to be met in the food packaging space. So the ultimate goal is to remove 100% of the nylon and then replace it with metallocene polyethylene in the bulk layer to maintain properties of these packages. By removing the nylon, we are increasing the potential for recyclability of these packages, and that's really the major driver for the work that was undertaken here. In the past, we have done some work in the area of blown films and water quench films with the intent of reducing nylon content and offered some solutions in that space. The scope of this work that I'm about to discuss was only on cast barrier films. And as I mentioned earlier, this market space in the cast barrier film seems to enjoy a larger market share in US, Canada, and Europe. This is a highly complex space technically, and a lot of attributes need to be met when these films are converted into thermoformable bottom webs. The first and foremost is the thermoformability of the package itself. So you don't want any significant thinning of the corner or the bottom layer of the package when the nylon is removed. The second is maintaining the toughness and abrasion resistance. And we are measuring puncture strength and taking that as a measure of toughness of the package. Many film converters are also using ISTA transportation tests, such as shaker table tests, to measure the abrasion resistance of the packages, which give an idea of the shipping process or the transportation process. Optical properties are also important. Having low haze and high clarity are important so that you can see, the consumers can see the food that's packaged inside. You also want to maintain a good balance of toughness and stiffness, and certain stiffness is required for these packages to maintain rigidity and hand feel and also cuttability during the thermoforming operation. And of course, you want to maintain a good barrier to oxygen and moisture to preserve the meat and cheese that's packaged inside. And you also want to maintain the flavor and aroma of the food packaged. Here are some typical structures that are used. On the left side, I'm showing a reference structure, which is a close approximation of what's used in the industry. It's a 9-layer structure with a total gauge of 7 mil. And layer 1 is a sealant layer shown in the light green color. And then there are 3 bulk layers shown in the darker green color, which are layers 2, 8, and 9. And there are 2 tie layers, which are layers 3 and 7. And then there were 2 nylon layers, layers 4 and 6, and an EVOH layer sandwiched between the 2 nylon layers. And the tie layers, shown in yellow here, are used to tie the bulk PE layer to the nylon layers. On the right, I'm showing the newer structures that we made with either 25% or 50% nylon reduction. And we achieved this by reducing the thickness of the nylon layer and increasing the thickness of the bulk PE layer, mainly layers 2 and 8, while keeping the overall gauge same at 7 mil. I'll talk about the details of the film structure a little bit later in this presentation. Now, coming to the actual trials we ran, we conducted the film trials, the cast barrier film trials at WNH at their lab in Germany. So we made the 9-layer structures using an 11-layer cast barrier Filmex line at WNH R&D Center in Langersch, Germany. And Nick Nigro from WNH will cover the details of that film line shortly. We used a film gauge of 7 mil, and the final film width was 20 inches. We made a reference structure with the full nylon content, and then we made some structures with 25% reduction in nylon content and some structures with 50% reduced nylon content. We measured a variety of physical properties of these films, but I'm going to focus on needle puncture strength as a measure of toughness of these films. And then I will focus on haze as a measure of optical properties of these films. We took these films to a third-party OEM and conducted thermoforming trials there. We used a draw depth of 8 centimeters or 80 millimeters, which is considered a deep draw. The temperature of 90 degrees C was used for thermoforming, and heating time of 2 seconds was used. We measured needle puncture strength on the thermoformed webs, and then we measured the corner thickness of the formed webs as well. The schematic on the right shows where we measured the different thicknesses. So 0.4 is where we measured the corner thickness, and 0.5 is where we measured the bottom layer thickness. Now I'm going to hand over the control to Nick Nigro from WNH to describe their cast barrier film and discuss the trials that were conducted at their R&D center.
Thank you, Nilesh. Good day, everyone. My name is Nick Nigro, and I'm product manager for extrusion in North America for WNH. And I'd like to speak to you today about the WNH cast extrusion lines and our technology center in Germany. In addition to our cast line, the facility houses 5 blown film lines, several printing presses, and an array of converting equipment. This equipment is available for customer demonstrations and trials, as well as WNH internal production and R&D. We were able to accomplish Exxon's goals using this cast line, which is well equipped and a fully capable production machine, and was easily up to the task. As you can see depicted here, it's equipped with 9 extruders, 1 for encapsulation if necessary. All of our extruders have our universal SMB2 screws. We utilize chlorine feed blocks and dies, and they're equipped with decals. And the line is also equipped with inline fluff feeding, dual gauging, corona treatment, and an array of modules to enhance the process capabilities. Next slide, please. So as with the Exxon trials, which required many format and resin changes in a short amount of time, these are also the challenges facing cast film producers today. While the cast film process is uniquely suited for long sustained production runs and campaigns, this is not always the case today. The dynamics and competition in the markets have increased the demands for larger varieties of film formats, smaller production runs, highly customized products, decreased certain raw material types as we attempted to do here with the Exxon trials, decreased quality additives with the introductions of post-consumer reclaim and post-industrial reclaim, and also the need for higher refeed rates. Consequently, if you want to produce in today's markets, you need to be flexible and you have to maintain faster and easier production changeovers in order to limit the waste and increase the profitability. Next slide, please. Although now faced with these challenges, the cast film producers' production goals haven't changed. You still need to be efficient and effective. You still need to have more uptime than downtime. You still need to have less scrap and waste. And you still need consistent film quality, roll to roll and run to run. So ultimately, you need to satisfy your customer and operate profitably. Increasing uptime and consistency is going to be the challenge, but necessity is required to do this. Next slide, please. Unfortunately, the industry is hampered with old equipment and machine technologies, as well as outdated process techniques. Once a line is honed in and stable, most manufacturers can manage even with these deficiencies, although not optimal. So more and more film producers find themselves in a position and are forced to consider some changes. Gauge changes take a lot of time. Format width changes may involve a decal change and operator intervention. Resin changes can also be very timely for it to get through the entire system, extruders and dies. The more changes of products and production runs require more lip cleaning and downtime. And then you have the die bolt adjustments, the edge pinning, and die mapping, which all require some manual intervention by the operators. These can all take hours and hours and cost hundreds of pounds of scrap before you can get to a saleable product. Next slide, please. So how can W&H help? It's always been the Windmiller directive to search for continuous improvements and address machine limitations and concerns. And while there's no doubt that our lines are certainly much more sophisticated than in the past, which is required, we've also considered operators and operator skills when optimizing our lines for ease of operation. So our goal was anyone can run these lines and achieve quality and output on a consistent basis. And with today's employment struggles and challenges, this becomes even more important. So we've done this with intuitive and ergonomic machine improvements, which allow for less operator intervention, reduced downtime modules, which enhance the process and allow quick startup and changeover. And most of these modules and add-ons can be tied to our recipes so that everything is downloadable to a recipe and then consistently called back at a future date. Enhanced production consistency is what the goal is, and these machine improvements and modules allow that to happen for uptime, reliability, and repeatability. We also have universal screw designs, which have proven to allow processing of multiple materials without the need for a screw change or utilize melt pumps or mixers. They can even process high percentages of fluff and reclaim, including PIR and PCR content. Additionally, the line is controlled by our Pro Control, which is a completely integrated control system and operator HMI, and it integrates all the components in the line with feedback to our operator. Lastly, we have our Ruby data capture and reporting system, which can allow processing of future improvements to individual campaigns and traceability to customers for process data. Next slide, please. And that brings us to our die control wizard. It's really not an overstatement to claim this improvement as revolutionary, because it's proven to be just that in every location that's been installed. Imagine eliminating operator intervention on many hands-on functions that they now perform. Simply enter the job on the onboard recipe list and let the machine do the rest. This enhancement includes fully automatic width and thickness change and control, rapid changeover without manual die bolt adjustment, without edge pinning or decals required manual assistance. And the automatic die bolt eliminates the need for any manual adjustments on the die after startup. So all of this significantly simplifies the complexity of the line and allows for faster and reproducible profile control, accelerates the startup, and gives you good production on a consistent basis. It enables processing of very challenging raw materials and also ensures safety of the personnel with less intervention. What literally took hours to accomplish before can be done in just minutes and is repeatable every time. Thank you.
Thanks, Nick. Shifting gears back now to the resin space, this slide shows the main polyethylene resins that were used during these trials. In the reference structure, we use Exceed 4518 as the main resin in the bulk layers, and this reference structure had the full nylon content. In the structures with 25 or 50% reduced nylon content, we use Exceed 2012 as a blend component in one structure, and we use Exceed XP 8784 as a blend component in another structure. The goal of using these resins was to boost the toughness of these films as nylon was removed from the structure. In one structure, we used EXT 348 at 3.5 mi and 9 Went density. This was a resin made at one of our pilot plants. And now this resin has been commercialized as Exceed XP 8346 PA at 3.5 mi and 916 density. So we have modified the resin slightly with lower density to fit the application needs. Again, the purpose of using this resin was to boost the toughness of the film. We use Exceed 3812 in the sealant layer of all of the films. On the next slide, I'll describe the actual composition of the bulk layers of various films. So for the reference film, we use Exceed 4518 for the bulk layers 2, 8, and 9. And this structure had the full nylon content, meaning the nylon layers were thicker compared to all the other structures. We had 3 structures with 25% reduced nylon content, and those were the structures A, B, and C shown here. Structure A had EXT 348 in the bulk layers. Structure B had a blend of 70% Exceed 4518 and 30% Exceed 2012, while structure C had a blend of 70% Exceed 4518 and 30% Exceed XP 8784 in the bulk layers. We had one structure with 50% reduced nylon content, and that structure D contained a 70-30 blend of Exceed 4518 and Exceed 3012. Now we come to the properties of the filmed and formed webs with 25% nylon reduction content. On the left here, I'm showing the properties of the films. So the light green bars represent the needle puncture strength, and the red circles represent the haze values of the films. What we observe is that the structure A with EXT 348 had higher needle puncture than the reference, while structure C with Exceed XP 8784 had similar needle puncture as the reference structure. And structure B with Exceed 2012 had slightly lower, about 10% lower needle puncture than the reference. Overall, all of these films have needle puncture values similar to that of the reference. When we look at the haze values, we see that structure C had slightly lower haze than the reference, while structures A and B had slightly higher, about 2 to 3% higher haze than the reference. But overall, the haze values were within the acceptable range for all the structures. On the right, I'm showing the properties for the thermoform webs. We use the draw depth of 8 centimeters, which is considered as deep draw. And here, the dark green bars represent the needle puncture strength, and the blue triangles represent the corner thickness. But we see that for needle puncture of all these structures is a little bit lower, about 10 to 15% lower than that of the reference. So it's still within the acceptable range for the puncture strength. And more importantly, the corner thickness of the structures A, B, and C is similar to that of the reference. So the corner thickness was maintained even though the 25% of nylon was removed from these structures. Now we come to the properties for the structures with 50% reduced nylon content. And here on the left, I'm showing the properties of the films. The light blue bars are for puncture strength. And what we see is the structure D with 50% less nylon has lower puncture than the reference. And it's about 20% lower. So we do lose more puncture strength here, particularly when you compare it to the films with 25% reduced nylon content. But when we look at the haze value, we see that the haze of the structure D is very similar to that of the reference. On the right, I am showing the properties of the form webs with 50% nylon reduction. And the dark blue bars are for puncture strength, and the green triangles represent corner thickness. Again, we see that the puncture strength of structure D is about 20% lower than that of the reference. So we do lose more puncture strength as we remove more nylon, and that might be a compromise that needs to be made. Again, when we look at the corner thickness shown by green triangles here, we see that the corner thickness was maintained fairly well even after removing 50% nylon from these structures. So overall, what we concluded from this study was that the corner thickness of the structures was maintained even when we used deep draw at 8 centimeters, and even after we removed 25 and 50% nylon from these structures. We also maintained the optical properties as seen in haze values of the films shown before. So what we observed that in most cases, the haze was similar, or we saw about 2 to 3% increase in haze versus the reference, which was within the acceptable range for haze. The puncture strength of films, particularly the films with 25% nylon reduction, was similar to that of the reference. And when we looked at the puncture strength of the formed webs, we saw that with 25% nylon reduction, the puncture strength was a little bit reduced versus the reference, but it was still in the acceptable range. But for the form web with 50% nylon reduction, we do see more reduction in puncture strength, and that might be a compromise that needs to be made as you remove as much as 50% nylon from these structures. So overall, what we concluded that it was possible to achieve 25% reduction in nylon content, and in some cases, 50% reduction in nylon content of the cast barrier films when you make the right choice of performance polyethylene resins from ExxonMobil. Now I'm going to talk about our next steps, and we are going to continue looking at the newer polymers that we are developing. One of them is the Exceed XP8346PA I mentioned earlier. On the left, I'm showing the rheology data for this resin, comparing it to Exceed 4518 and 3518, which are two of the most commonly used Exceed resins in the cast film space. What we see is that this resin shown by the purple curve is more shear thinning than either of the Exceed resins, which means that its viscosity is lower, particularly at the higher shear rates or higher frequencies compared to the two Exceed resins. And this is highly desirable because many film converters want the resin to move very quickly to the edge of the die and give very good flow properties. On the right, I am showing the mechanical properties or physical properties of these films. And what you see is the mechanical properties like dart drop, MD tear, and TD tear are significantly higher for Exceed XP8346 versus the Exceed 3518. So when you use this new resin, we expect the mechanical properties to be increased for the films. Finally, we come to the current solutions proposed and the path forward in the space of cast barrier films. What we would propose as current potential solution, if you want to 25 to 50% nylon from the cast barrier films. One is a blend of Exceed 2012 with Exceed 4518. Another possibility is using Exceed XP8784 as a blend component. as long as you can process and handle a 0.8 mi resin on your cast film line. In terms of path forward, we will continue evaluating new polymers like Exceed XP 8346PA that I just mentioned. And this resin is just variation of the pilot plant resin EXT348 that was discussed in this presentation. We will also evaluate some newer products that we are developing right now. And these products offer a unique balance of toughness and stiffness that goes beyond anything we are offering in our portfolio today. In addition, we want to evaluate nylon-free structures, that is, structures that have 100% nylon removed. And these are much more challenging as compared to the structures with 25 to 50% nylon removal. And we also want to explore options to improve the abrasion resistance of the outer layer. So we want to continue looking at higher density polyethylenes as well as some polypropylene resins. And that's all I have to offer here. And thank you for your attention.